Hi everyone, my name is Girish and I'm going to cover today what I call the universal physics cheat. This is a method called unit analysis, and oftentimes it can provide clues as to how to apply a particular formula in a problem, or even how to derive a formula that you might have forgotten. So to cover this unit analysis, I'm going to take an example, and in this example, I've taken Alex Dunphy, who's one of the characters from Modern Family, and she's just about to go to college. She's in fact on her first day, and she's moving into her freshman dorm. So she's come to her freshman dorm. There's her freshman dorm, and she's outside her freshman dorm with her two suitcases. And each of these suitcases require 300 newtons of force for Alex to pick up the suitcase and take it into the dorm. And she has to move those suitcases up onto the third floor of this dorm. And so the height of the third floor is 10 meters. So she has to apply 300 newtons of force on each of these suitcases, each of these two suitcases, and move it up 10 meters. And the question is, what amount of work has Alex done? What amount of work will Alex have to do in joules in order to move these suitcases up into her dorm room? Okay, so this is great. This is a fairly straightforward question if you know what the formula for work is. But I'm on this test and I've forgotten the formula for work. So at this point, without knowing the formula for work, I'm pretty stuck. So the first thing I do is I go back to my universal physics cheat and I see what can unit analysis do for me in this situation. So what I'm going to do is look at the units in this problem and try and understand those a little bit better. So the first thing I'm going to do is I'm going to actually reach back into my memory and I'm going to say, okay, what do I know about all these quantities? If there's a force of 300 newtons, well, I don't know what newtons are, but I do know something about force. I do remember from way back that it was drilled into me that force is equal to ma, that F is equal to ma, mass times acceleration. Okay, so that's one thing I know. Another thing I know is that I have come across an energy equation before, which was also listed in joules. So there's no listing of energy here, but there is a listing of joules. And I have seen an energy equation before that is listed in joules. And I remember from, again, way back that kinetic energy is sometimes described as 1/2 mv squared. Okay, so that's something else that I know, and I also know that this quantity, which is energy, can also be measured in joules. Okay, so I'm going to write these things down in terms of their units. I'm not going to worry about what the values are, and I'm also not going to worry about things like, is this formula applicable to this problem? I'm right now just focusing on the units. Okay. Okay. So I know that if this energy formula can be described in joules, and this formula is mass times velocity squared. Whatever the units are of this mass times velocity squared, they must be equivalent to the units of joules. So first thing I'm going to do is figure out what are these units. Okay. So step one is to figure out the units of 1/2 and mass times velocity squared. Okay. So mass is just grams or kilograms. So I'm going to write down kilograms. Then there's a times and a velocity squared. So velocity is meters over seconds. So velocity squared would be meters squared over seconds squared. Okay. So now I figured out what the units are of this particular equation right here, and those units must be equivalent to joules because energy is also measured in joules. And I remember that energy is measured in joules also because I remember looking at the back of food packets, and on the back of food packets where you're looking at the calories, it sometimes shows the energy in calories, but it sometimes shows it in joules also. Okay. Okay, so joules can also be written as kilograms times meters squared over seconds squared. Okay, so I still don't know what the formula for work is, but I feel like I'm on some kind of path that might help me figure it out. Now the other part of this equation is force, and this is described in newtons, which again I don't know what newtons really means, but I do know that force is equal to mass times acceleration. So let me figure out the units of mass times acceleration. Okay, so if we try and figure out the units of mass times acceleration, what we get is that newtons must be equal to mass, which is kilograms over here, times acceleration, which is meters per second squared. So if I take out this square here, then mass, which is kilograms or grams, times acceleration, which is meters per second squared, must be equal to newtons, or be describable in some way in the units of newtons. Now, as an aside, I said that acceleration was meters per second squared, and that I remembered that. But what if I didn't remember that acceleration was meters per second squared? I could do the same kind of thing with acceleration also. So I could, if I didn't know the units of acceleration, I could say, okay, well, acceleration is equal to velocity over time. That I do know. So if acceleration is velocity over time, that's meters per second per time per second again. So that would then come out to be meters per second squared. Well, we know force is in newtons, and that's kilograms times meters per second squared. And we know that the answer needs to be in joules, which is kilograms times meter squared per second squared. So what we're missing here is just a meters on the numerator. If we can multiply this thing, this quantity with the meters, we would get the same units as the answer that we're looking for. So this units represents force, so let's write that down. And what we're missing is a meters, like we have over here, which is just a type of distance. And that would equal what we're looking for in joules, which is work. And so we actually have derived the formula for work. Work is equal to force times distance, and is in the formula is in the units of Newton meters, which is also equal to joules. Okay, so if we multiply this through the 600 newtons of force that Alex has to apply to carry both of her suitcases, and she has to do it 10 meters up to get to her room, so the total for this answer would be 6,000 joules. Okay, so that's unit analysis, and we've actually used it to do something quite complicated. We've used it to derive a formula on the spot. Now, I want to just very quickly show you some of the flexibility around this approach and other things that you could have done in the problem if the problem was slightly different. Okay, so for example, let's assume for a second that I didn't know that E equals 1/2 mv squared. I didn't remember that particular energy equation. I remembered a different one, and in this case I remembered E equals mc squared, where c is the speed of light. Well, I can do the same thing, and I can say, okay, E equals m is mass is kilograms, speed of light is a velocity, which is mass over which is meters over seconds squared, and it comes out to the same thing, kilogram meter squared over second squared, which is the same as joules. And if I didn't remember that, maybe I remembered from the olden days the potential energy equation, which is mgh. So if you remember when we had those problems where a ball was at a certain height at rest and you let it go and gravity brought it down, what was the total amount of potential energy in the ball before it came down? That was that mgh formula. And again, if you apply the same rules, m is mass, that's kilograms, g is gravity, that's meters per second squared, and height is just a distance, so that's meters. Again, you get kilogram meters squared per second squared. Okay, so you could have done this with any one of the energy equations, because at the end of the day, all of the energy units have to be able to be seen in the same way. Okay. Now, let's assume that we didn't get the benefit of knowing that that Alex used 300 newtons of force on each one of her suitcases. Instead, we got something like she had 30 kilogram suitcases, and she had to move up 10 meters. Now, in this case, we have no units of force. So we may even know that work is equal to force times distance, but in this case, we have no force to work with. So in case we didn't remember and didn't kind of put together that we had to come up with what the missing elements were, we could still use unit analysis to do the same kind of approach. So we have kilograms times meters. And what we basically need is another meters per second squared in order to get the magic units that we're looking for. And so then that allows us to look at meters per second squared and say, okay, that's an acceleration. And hopefully that jogs our memory to say, okay, well, gravity is an acceleration, and it makes sense that Alex would have to fight gravity, the force of gravity, to in order to get her suitcases up to her room. So then again, we can go through very quickly and do 30 kilograms times 9.8 meters per second squared, which is the gravitational constant. And we come up with 294 newtons, which is very close to 300 newtons we were given in the problem. So in this problem, we actually knew the formula, but we just didn't know how to apply it. But still, we could use units analysis to get a clue as to how to go forward in the problem. In this problem, we just saw that many different equations yielded us to the same result, which allowed us to go on in the problem. And in the first part of the problem, we saw that we could derive the formula on the spot. So I hope that gives a little background on what unit analysis actually is and some of the ways in which it can be used. Now, I'm done showing unit analysis, but I am, for anybody who's interested, I'm just going to go on a little bit to show an example of a case where unit analysis can be used even when you may not know what the equation is. Okay, so in the last example, we're going to look at an equation which you may or may not have come across before. This is Bernoulli's principle, and it's actually a very powerful equation in fluid mechanics that relates to energy in fluids. So if you get Bernoulli's principle right, which is this Bernoulli's principle, you can do things like understand how a plane flies. If you get it wrong and you apply it wrong, not so much. Okay, so we're going to go through and try and understand which of these equations is right. Now we know that this is the right equation, but I'm going to show how, even if you didn't know which was the right equation, how you would figure it out. Okay. So the only thing we need to know is that equations need to be internally consistent. So you can add meters to meters to meters, but you can't add meters to cows to pigs, for example. So you need to be able to know that the units of each of these terms are the same. So that gives us a starting point. What we can do is we can look at, say, the units of this first term, and which is in both equations, and figure what those out, and those must be the units for every other term also. Okay, so this funny looking P symbol actually stands for rho, and rho is just the density of the fluid. So density is just a mass times the volume. Okay, So we'll start with that. Density is equal to mass over volume. The next term is gravity, and that's just an acceleration. And then the final term is h, which is a distance. Okay, so let's write that out now in its units. Well, the first unit is mass over volume, so that's kilogram over meters cubed. And we want to multiply that by an acceleration, which is meters per second squared. And then lastly, we want to multiply by distance, which is another meters. So we cancel out what we can cancel out, and we end up with kilogram over meters times second squared. Now that must be the units for every term in this equation in order for the equation to be internally consistent. So we're going to look at the next term here, which is the rho v squared, and is also the term in question because that's a term that differs from the other formula. Okay, so rho is once again kilograms per meters cubed, and it is multiplied by velocity, which is meters per second squared, is meters squared per second squared. Again, cancel out what we can cancel out here, and we get the same kilogram over meters per second squared. So we know that these two terms have the same units and are internally consistent, and that this could be the right equation, but that this definitely could not be, because here the A term for area would add an extra meter squared to the numerator, and we would get kilogram meter squared over second squared, which actually we've seen before is the units for joules, and not the units that we're dealing with here. Okay, so we know this is the right equation and this is the wrong equation, which I think is pretty cool that we were able to do this even maybe having never seen the equations before. Okay. Okay, one last really cool thing. You see this last term, P, that stands for pressure. So now we know that pressure, by default, has to have the same units, kilograms over meters per second squared. Pressure is also in terms of pascals. So pascals must also have kilograms per meter squared. So pressure in Pascal units must be kilograms over meters times second squared. The really cool thing is, now even without ever having studied it, we can go back and say, hey, we know that Newton is kilogram meters over second squared and joules is kilogram meter squared over second squared. So we can look at this pressure term and say, okay, well, if we add a meter squared on top of here, because now we're experts with unit analysis, if we add a meter squared on top of here, that would cancel out with the meters here, and we'd have kilogram meters over second squared, which is force. So a meter squared on top is just an area. So that means that pressure times area is equal to force. So if you apply pressure at an area, you are that will be translated into a force. What's more is that pressure times volume, which is adding in extra meters on top of it, would then give you kilogram meters squared over second squared, which we know is the units for work. So pressure times volume actually equals work. This is the reason why at the end of all of this, I refer to unit analysis as the universal physics cheat. Okay, good luck. I don't recommend that you do unit analysis for the very first time on a test, but if you try it on problem sets or within your homework, then hopefully someday it'll also be able to save you like it has me on an exam. Good luck.